Yoda, my name is Amanda, and I'll be teaching you about capacitors in our electrical system standard level 3 physics. First off, what do you know about capacitors? Yeah, yeah. Two parallel plates, you're right. And precisely what a capacitor does is it stores and releases energy through the form of electric field. This is different from your usual battery source, which stores electric energy as chemical potential energy. And as you said, there are two parallel plates which are conductive that make up a capacitor. And those two plates are separated by dielectric. And I'll explain what a dielectric is very soon. Do you know what a dielectric is? Not yet. Okay. We will find out. So now I'm just showing you three quite fundamental formulae that's associated with the whole definition of capacitance and capacitors. So you can see Q equals CV, which defines capacitance as a capacitor's ability to store charge per volt. And the energy is proportional to the charge and the volt in a capacitor. Okay. And the third formula that you see here, E naught is constant. ER is the permittivity of the dielectric material. A and D are both physical properties of the parallel plates. So physical dimensions rather, area and distance that determines the capacitance of a capacitor. Okay, and back to the definition of a dielectric. It's the opposite to a conductive material. It's a material that doesn't conduct electric current but can support an electric field by becoming polarized. So the charges in a dielectric does shift, but it doesn't allow a current to pass through. That's how a capacitor can become charged. Moving on, you can see on the right, this quite handsome fella is called microfaraday. And the reason why he's here is because the unit for capacitance is Faraday, right? It's F. So as I've mentioned before, Q equals CV is the fundamental formula for capacitance, and it is the ability to store charge per volt. So Q is charge measured in coulombs, C. V stands for voltage, and it's measured in volts, V. And the energy equation, E, is an old friend, it's measured in joules. Does this formula look familiar to you? A little bit? Yeah, good. Cool. Yeah. So, this formula, that funny little Greek character tau, stands for time constants. So it describes time constants in a circuit with resistor and capacitor. Obviously, R for resistance measured in ohms and C for capacitance. Each tau, each time constant, means that the capacitor is charged by 63% to its maximum charge, or if it's discharging, it's discharged to 37% off its original charge. So when you're looking at these two graphs of a charging capacitor and a discharging capacitor, what do you notice about this shape and gradient of the graph? Yep, you're right. Mhm. So the change looks steeper at the beginning, right, initially, whether that's increasing or decreasing, and then it tends to plateau a little bit um, when there's enough time passing. Okay. And so to fully explain why, I'm going to bring you to a little circuit lab. Okay, so the setup over here is we've got a battery, a source voltage, we've got wire, we've got the capacitor, a resistor over here, and a switch. And maybe it's more straightforward if I change it to this view, eh? Yeah, cool. And I'm going to change it back just so it's viewed better. And on here, we are going to see electrons moving. So this is not conventional current. It is the actual direction of the electron moving, right? So which direction does the electrons move in a circuit? Is it from the negative terminal to the positive terminal of battery, or is it the other way around? Be careful, that's conventional current. Yeah, yeah. So it's from negative terminal to a positive terminal. And what do you think will happen after I close the switch, right? When the circuit becomes complete? Yeah, yes, precisely. Yeah. So the capacitor is going to be charged. And I have this voltage chart here to record the voltage changes. So now I'm going to hit play and close the switch, and we'll see what happens. Okay. So you see, interesting. Yep. So you can see the change graph here, similar to what I showed you on the slide. And over here, you have on the left is a negative plate, on the right is a positive plate. Why is that so, do you think? Hmm. Yeah. So the negative charges, right, are crammed onto this left plate here. And negative charges on the right plate are pulled away. So it becomes positively charged on the right plate. And in the beginning, when the switch is just closed, the change is big, right? The current goes from zero to maximum quite quickly, and it's drawn by the voltage across this resistor. But as time goes by, the change slows down because the negative plate becomes more negatively charged, and there's a natural repulsive force, mutually repulsive force, between the negative plate and the incoming electrons. So that slows down. And also, we know that voltage is the potential difference between 2 points. And now that the two parallel plates of capacitor is differently charged, there's definitely a potential difference between the two, right? But it's not actually along the direction of the source voltage's current. It's a it's an opposing voltage. So you can see that if we cut these and connect that, and you will see the capacitor quickly discharge. See how it's going the other way? It's going counterclockwise now. Yeah, so it's discharged sort of now. Yeah, cool. So going back to our slide over here, a capacitor cannot be 100% charged or discharged, but we consider it as almost 100% after 5 time constants. So that's something to remember. Your magic percentage, 63% and 5 T's. Now let's look at an exam question. This is 2023 and it's E question. Now don't panic when you see a super long question. It's easy when you break it down. So I'm going to show you my tips. When you walk into an exam and you start reading a question, there's a checklist. What is the question? So I would go around using a highlighter to highlight what information does it require from me. And then what do I know from the question? What information is given? what unit conversions do I need to do? And then when you're trying to work out the answer, make sure to show formula so you don't confuse yourself, show working so you don't confuse your examiner. And once you got the answer, to check your unit and significant figures. So with science, you need to match your significant figure with the one that's given in the exam question. And the last step is a dummy check. So is the number supposed to be increasing? Is it supposed to be decreasing? Does it seem right in terms of the relationship of the formula? Um, whether it's proportional or inversely proportional. Cool. So going back to the question, reading, reading, reading. So what is it asking for? It wants a curve with at least 4 points. And we can see that on the graph paper, it's asking for charge against time. So we need 4 calculations for that. Your answer should also indicate the time constant, the t, and the maximum charge that will be stored. So Qmax. Okay, so here's the information we've collected so far. We want T, we want Qmax, we want 4 data points, and we know the resistance of the resistor was 0.27 ohms. The voltage of the source was 1.5 volts, and the capacitance is 185. Now, looking at NF, do you remember the standard form that N stands for, your metric conversions? Not quite 10 to the negative 6, no. That's micro. Okay, micro and nano are often confused together. So when you see an N, it'll be nano. Looking at this table here, right? So micro is the mu sign, 10 to the negative 6, and nano is N sign, so N to the negative 9. Cool. So remember, it's sort of a unit conversion, converting it into standard form 185 times 10 to the negative 9, because we want it in Faradays and not nanofarads. Yep. Now, using what we know the resistance, we know the capacitance, we can immediately find the time constants, right? So time equals T equals to RC, T equals to plugging in the value 0.27 times 185 times 10 to the negative 9. And the answer comes to this. Do you think it's right? You're not sure? Is it right? You think it's right? Hmm, I think it's missing something. Significant figures and unit. So 5, there's only one significant figure, which doesn't match with the number given here, you know. And the unit, missing a unit. T, what's T measured in? Cool, so now it's complete. 5.00, that's 3 significant figures, times 10 to the negative 8 seconds. Now moving on, we've got the T to Qmax. We have the formula Q equals to CV, right? The fundamental capacitance formula. So Q equals to, you plug in the C value times plug in the V value, 2.78 times 10 to the negative 7. Is that right? Yes, yes. So it's still missing a unit, right? Unit for Q is coulombs. So 27.8 times 10 to the negative 8 coulombs. The reason why I changed it from to the negative 7 to the negative 8 is because that's the value we are plotting on the graph, right? Notice here is 10 to the negative 8. Now we need 4 data points. So in order for us to complete a good dummy check at the end, we need to know, is our capacitor charging or discharging? What do you think? When the switch closes. Yep, so it's charging, right? It should go from 0 to plateau to a value that's very close to Qmax. Right. So after 1t, when time equals to what we calculated, 5 to the negative 8, what is Q? Remember the magic percentage? 63%? Yep. So this is kind of a formula. Q equals to Q maximum times 1 take away 0.37 to the power of n. N stands for how many time constants that's been. So, 1 take away 0.37 is 0.63, which is 63%, which is how much to the Qmax the capacitor is charged by after one time constant. Okay, so plugging in the values again, nice and easy. You get 17.5 times 10 to the negative 8. Good luck. Nice. We do the same for 2t. So that is when you grab the t value and you times it by 2, naturally we get 10 to the negative 8. What is q? The same old formula, but now after two time constants, the n will be 2, right? Yep. 24 times 10 to the negative 8. Notice how it's getting bigger and closer to Qmax? Yep, that's your dummy check coming in. So that makes sense overall, right? So let's keep going. Can you do 3t and 4t on your own? I'll give you some time. Mm-hmm. Yep. You ready for an answer reveal? Cool. So after 3t, when time is 15 to the negative 8, charge is 26.4 to the negative 8 coulombs. After 4t, when time is 20 to the negative 8, your charge is 27.3 to the negative 8. You got this right? Perfect. Okay, so you've handled a E question very well and you've packed all of your E points in. Cool. Not yet, sorry. Now we need to plug in the data points. So we've got 5, 10, 15, and 20. Plugging in. I would actually prefer a cross instead of a dot here, but a dot is easier to do, I suppose. A cross, and it's supposed to give you an exponential growth shape. Perfect. Now you've packed in all the E points. And let's go back to exam checklist again. So remember, next time you see a question, don't panic. Think about what is the question asking for? What do I already know? Unit conversions. Show formula, show working, show unit, and significant figures. And at the end, dummy check. Thank you very much. Have a nice rest of your day.